Welcome to this demonstration of CS454 Vehicle Load Optimization, available in LUSAS from version 18.1. The model I'm using for this demonstration is a free-span slab bridge modelled with shell elements. Over this skew-ended bridge we have a curved carriageway with these two lines defining the curb lines or edges of the carriageway. In order to carry out a vehicle load optimization, the first thing to do is to define an influence of the effect we'd like to optimize for. For this example, I'm just going to be looking at bending moment mx. In a real-life example, you would probably be looking at multiple effects, but in order to keep this demonstration simple, I'm only looking at one. We then need to select which parts of the model we want to optimize the effect for. Again, I'm only selecting a few in order to make this demonstration quick and simple. We then need to assign the influence to these selected locations. In order to carry out the load optimization, we then need to select our curb lines and go to Bridge, Vehicle Load Optimization. We then need to select our design code. We've implemented both CS454 Model 1 and Model 2 within LUSAS. If we select Model 1 first and look at the optional settings, we can see that we can choose whether to optimize for single vehicle only with a dynamic factor on the most critical axle, or a convoy, multiple vehicles with no dynamic factor. Most likely we want LUSAS to consider both of them and then give us the worst of the two. We can also change the traffic flow, surface quality and the load level if we wish to. If we then choose which influences we're optimizing for, and because I want sagging on the central spans and hogging over the supports, I'm going to set it up with negative for the spans. I'm going to create loading patterns as well as see the table. Click Define Carriageways to let LUSAS know that the lines I selected are the curb lines, and click OK to run the optimization. We can see in the table that's generated the hogging moment that LUSAS has been able to find, maximum of 295.7 kN meters per meter width. And looking at sagging, we can see we found 290 in the main span and 250 in the shorter end span. If we then look at the load cases that have been generated, we can see that for sagging in the end span, we've got one vehicle in each lane, and that vehicle is vehicle A. Looking at the load pattern for sagging in the main span, again we have one vehicle per lane. This time it's found that vehicle D2 is the most onerous. Looking at the hogging load patterns, we can see that we've got a convoy of vehicles, and the vehicle that's being used is vehicle A. And that's the same for the other hogging pattern as well. Alternatively, if we had decided that this bridge was suitable for Model 2 rather than Model 1, we could also run the vehicle load optimization for that, this time selecting Model 2. If we click on the optional settings, we can see that we can include HB loading to Appendix C if our client is requiring it. We'll stick with normal traffic and with high traffic flow and poor surface quality. We'll use the table in the code to decide the number of traffic lanes on the bridge. We'll then need to set the influence surfaces the same as last time. We'll tick to create loading patterns and define the carriageways. This time we can see a maximum hogging moment of 218 kN meters per meter, maximum sagging of 265. If we look at the load patterns that have been generated, we can see we've got our UDL with our KEL in span 1 for sagging in span 1, obviously the same in span 2 for span 2, and when we're looking at hogging we've got both spans loaded as we'd expect. Obviously on a real structure you'd determine in advance whether it was Model 1 or Model 2 rather than checking both.